All right, welcome back to session 2. Oh, okay. So, power factor correction. All right. So let's just quickly let's go back to this motor, right? So let's just consider that single phase induction motor, right, or even three phase, doesn't really matter, right? And we obviously know that if the motor is coupled to this supply going to the motor, and they're saying if the motor presented a purely resistive load to the supply, which it doesn't, but if it did, the current would have been in phase with the voltage. What do you mean that sine wave, or the current sine wave, voltage sine wave would have been like superimposed on each other, right? But obviously this is not the case. They're out of phase, so they have a difference in degrees, which is essentially demonstrated there. So what they say is that the motor has a magnet and a magnetizing current and is not in phase with the voltage. Obviously, I just mentioned that. The magnetizing current is the current that establishes the flux in the iron, and being out of phase causes the shaft motor to rotate. So when we have the magnet, electromagnet, and we're running current through, it generates a flux, and obviously or electromagnetic field. And like I said, that is for that essentially produces that Q, so that you could have the electromagnetic field. And obviously this is this is what they're referring to the magnetizing current. And they're saying there the magnetizing current is independent of the load. Obviously we're aware of that because S has two components, the P and the Q. And obviously Q is the foam on the beer or the air in the Lay's packet of chips. And what they say is that typically the motor will be between 20 to 60% of the rated full current of the thing. So we don't actually use all the current, and a certain amount of the current is lost because of the magnetizing current, which is obviously used for the magnetic field. And what they do, what they lastly state that the magnetizing current slash the reactive power does not contribute to the work output of the motor. So we're obviously aware of this. So we know that there's a lag. Okay. So this lag, I think I feel like I'm missing something here. Yeah. Okay, so this lag is obviously what we don't want. We want the full amount of current. And we've obviously discussed what the power factor is. So how do we correct this power factor? First of all, what is power factor correction? So factor correction there, as stated there, it's basically to restore the power factor to as close as unity as possible. Like I said, power factor is a measure of electrical energy efficiency or electrical supply efficiency. And what we essentially want to do is bring it all the way up. And they're saying this is normally achieved by the addition of capacitors to the electrical network, which will compensate for the reactive power demand on the inductive load. So yeah, that's the essential way. So why do we want to improve the power factor? First of all, well, there's obviously reasons, just kind of reading on here, but there's environmental benefit and the reduction of power consumption due to energy efficiency. Obviously, the idea is that we making sure the equipment is operated on a higher, like it's more efficient. And obviously, in turn, it'll obviously have environmental benefits, concurrent environmental benefits. Same thing. The other thing is reduction in bills. So typically, if you own a factory, you get charged for kVA and not for kilowatt like the normal consumers. Obviously, this doesn't apply to onboard a ship, but obviously it applies to the first point I've mentioned. And obviously, this consequently, we also have extra kVA available for the supply. So if we can improve the factor, we actually can generate more power. They also say this, the reduction of I²R losses in the transformers and distribution equipment, and also reduces the voltage drop in long cables in particular. So there are a few benefits on why you want to improve power factor. Just as a quick demonstration, let me just quickly show you. Okay, why is it not opening now? I had a graph. It doesn't seem like it's loaded. Okay, it's starting, but anyway, that's fine. I'll get back to this. What did it on? Okay, so never mind that. I thought it was done. Okay, then just reverting back now. So this obviously is just the ways. There's a benefit of improving power factor. The most predominant ways now, not now. There is a more. I can't remember the other one now. The more latest one, but there are three of the most common ways to improve power factor is the use of synchronous motors, or capacitors, static capacitors, and phase advances. So I'll just quickly briefly go through this because there is some theory I want you guys to go over, which obviously act as some bonus marks in your test. I do believe as a chief engineer you need to be aware of power factor, because if power factors are poor, it'll be your job to obviously tell the ship manager or whatever when you get on dry dock or port to actually kind of fix that up. So I'll go to the first one. You have static capacitors. This is the most old school and the most cheapest way as far as I know. And how we do it essentially is the power factor is basically improved by capacitors in parallel with the operating equipment, which is obviously operating at the lagging power factor. So what we essentially do, we have a capacitor bank, and we hook it up to either the motor or at the supply to essentially improve the power factor, because as we know, capacitors provide a leading power factor or positive reactive power, and obviously that kind of compensates for that negative Q, so to say. What they do state there, so the capacitor typically, the static capacitors, throws a leading current or partly or completely neutralizes the lagging reactive component of the load current, right? And this in turn raises the capacitor of the load. So for three-phase loads, we either have it as in star or delta, which I'll talk about. I should actually talk about it. I should actually go to that slide now after this. But anyway, the advantage they have low losses, little maintenance, no rotating parts as the capacitor bank. They're light and they can work essentially in any condition. The only problem is they have a short life service. That's arguably 8 to 10 years is quite fine. This could be actually shorter or longer now. They easily damage if the voltage exceeds the rated value, if that does happen, and also the damage, the repair is uneconomical, and what essentially means you have to put in new capacitors. So so that's what a typical capacitor bank looks like. This is at the supply where they put it up. They put these 4 capacitors in, or I'm not sure exactly. There's a capacitor bank, each capacitor bank, to correct the power factor. But the graph what I want to show you is essentially that. So first of all, there's inductive load which pushes the voltage, the current away, and then power factor correction essentially brings it back. So inductive load pushes it out of phase, and when we apply the capacitor banks, it pushes it back again, going out, and then pushes it essentially back. It's basically making the sine wave, trying to make the sine wave as completely in phase, the current sine wave completely in phase with the voltage sine wave. Okay. Just another demonstration of this is you as you can see there, without the capacitor, well, it's quite different. I thought it'd be different, look different. But anyway, the idea is that we've got 2 motors, and then we have the active power with blue and the red power, the active power, and obviously the total power available would be that whole block. Then as you have a capacitor bank at the sketch below, it kind of improves the kVA of the thing. So that's the kind of idea we're looking at. Before I get to that, actually, I just want to make you guys aware. I think I should have put the slide somewhere else. I left it at the end because of the calculations, but for us to calculate how much capacitors we need, or the size of the capacitors rather, we have to use the change in Q divided by VL squared 2 pi F. What do I mean by the change in Q? The change in Q essentially the reactive power before minus now. So for instance, if you look at this diagram over here, what we actually do is that there's the total reactive power, just QC, and then once we add, or rather, think of it as QC, and once we add the capacitor, Q2, then creates a positive reactive power, And then obviously, so it'll be QC minus Q2, and you'll get Q1 will be our new reactive. So that Q1 is essentially the change in Q, and that's the model for it. But we have to be cognizant. So for star, we use that on top, but for delta, we have the 3 over there. There is a derivation for this, but obviously, I don't want to go into it. And what's important of this is that they stated the star, as with the star arrangement, 3 of these capacitors are required for the delta configuration. And basically, that comparing the two formula, we'll see in terms of star and delta, we see the star configuration will require three more times the capacitance. So typically, when you're connecting capacitor banks, wherever it may be, it's typically connected in a delta configuration, because obviously we have to pay more. If it's in star, then you have to obviously pay more. If you connect it in star, it'll be obviously more. So that's the idea. So the equation which we'll be using a lot is essentially the one at the bottom here with the 3 VL squared 2 pi f. And I know it comes in your formula sheet. So reverting into that, I might ask this as a bonus question. Who knows? And the question is, where do we install these capacitor banks to correct the power factor? And they state there, because the capacitors act as KVR generators, that's essentially true. The most efficient place to install them is directly at the motor, where the KVR is essentially consumed. So what they essentially explaining there is 3 different cases where you ideally want to connect it at the motor side of the overload relay, or the line side starter, or also location C. So you typically want to connect it close to the motor as possible in this case. So if you have the service feeder, or where the main bus is, you typically want to connect to capacitor bank. As what they say capacitor banks are installed at the service entrance if load, condition, and transformer size permit. If the amount of connection is too large, some capacitors can be stored at individual motors. So it's a two-way approach in terms of where you want to connect the capacitors. Typically at the motor, that's presenting its own thing, but typically they'll have it just at the main bus, or where at the supply is, just to give you some more clarity. What you see here, just give me a Thank you for your patience. Yeah, so what you're seeing over here is also a device where it's called an automatic power factor correction unit, which can be coupled to where the generators are, and they could actually not automatically obviously, but it corrects the power factor if it gets poorly. So there's a bunch of capacitor banks here, and if the power factor goes below a certain threshold, then this will kick in. So this is just an example of what I was referring to on the slide, where we had where what it would typically look like. So we typically connect it in delta, and the capacitor bank will be configured like that to the load in this case over here. Okay, so there is another mode, another way to correct power factors, and if we have time, we do synchronous motors, but I'll see. And synchronous motor is also can be used as a power factor correction, but if it is used, it's deemed a synchronous condenser. Right. So when we overly excite a synchronous motor, or what tends to happen, it produces a leading current, and then it will behave as a capacitor. So basically, this overexcited motor, when running on no load, acts as a capacitor. And if it's connected in parallel with the supply, it essentially takes a leading current, which and basically neutralizes the lagging part. So that's essentially, we might do it like I said, but this is typically used on a bigger scale. And the same synchronous condenser is generally used for major park supply stations for PET. So yeah, for like a bigger kind of setup, you want to use a synchronous motor to kind of correct the power factor. There's some advantages and disadvantages. I think I'll just talk about the disadvantages. There's losses obviously in the motor. It's a high maintenance, produces noise. It's a motor, and they're saying that except in sizes about 500 kVA, the cost is greater, obviously, and also the synchronous motor has no self-starting torque, and you have to produce it. You have to have insulated equipment to kind of kickstart the thing. So that's just for that. Also, phase advantages. which I won't really touch on, but you can have a read over this particular way. There is something else I'm forgetting. I just can't recall. So I'd like to ask you guys. This is just a slide where I get information from students. What is your experience with power factor correction in terms of equipment, especially like in the maritime space? Can I just open the floor here? I hope you guys are still listening. So let me just see if some opens. Mr. Plachis, see your name is here. Mr. Peters, Ms. Duba, Mr. Mambisa. What is your experience with power factor correction, or can you share any experience, please? Mr. Swanepoel, do you want to say something? Mr. Ball?
I only know that's considered during the ship design. I've never had to deal with it in a ship that's already been running. As long as if we're changing out a motor, the motor must just comply with the requirements. So the kVA and basically the physical size of it and the base plate. We don't really consider things like power factor.
Okay, cool. That's great. Installation of new motor. There's some thoughts I collect. Motor installation, ensure. Yeah, I know it has to obviously comply with whatever. Anyone else?
I haven't done any power factor correction on boats, but I know the company is quite strict about the plant's power factor because it plays a major role in the efficiency.
Yes, that's nice. Okay, cool. Essential power factors are standard. Anyone else? Comply to standard. Go for it. Free.
Yeah, so regards to like bigger engines like STX engines and stuff, they generally controlled by the governor and they're not controlled by frequency converters and stuff. So when you parallel the engines after some time, you have to like get it stable again. So once a month or once every 2 months, you have to put all the generators on load again and adjust their power factors to match each other. Otherwise, they come out of sync.
Nice. That's nice. That's nice. Yeah, and hopefully we'll touch on paralleling of synchronous alternators, which I have time for. Okay. Anyone else? You want to share your experience with power factors? Ooh. Okay, I think that's all. Okay, I want to include those notes. Okay, so what we're essentially going to do now is just basically do some computations with power factor, and then we're basically done for the day. Then I want to mention a few things about three-phase. Okay, so what we have here, then we will do this question. We have 2 loads, then increase the power factor. Then I'll just adding an extra part of this question, and we can also just do as well. And then you guys can have a look at all the other questions, especially the summary, and I'll talk about the assignment at the end. Okay. So we have a 3-phase motor, assuming it's just a 3-phase motor, and what we're going to be doing is, so should I have it something like this? 1, 2, 3, and what we're going to do is the motor is drawing 5 kilowatts at a power factor of 0.75, lagging obviously. And what we're going to do is put online, just like this, which I'll show you now. Just like that. So I'll just snip it here. We're connecting it in Delta to improve the power factor. So I'll just paste this here. Yeah, there we go. So something like that. So let me just essentially have this. I could have actually just used this as a drawing, right? So we have a 5 kilowatt motor, and the power factor is 0.75 lagging. Okay. So when we add the capacitor banks, it's going to provide a leading current, as I stated, positive reactive power, and it's going to raise the power factor to 0.75. They're asking what is the kVAR rating of the capacitors. In fact, we're going to find the actual individual power factor. What is this measurement? And I want to show you something on a separate note. I'll probably just paste it in the slide. If people actually would actually use, you know, to find them. Yeah, to find the, what is this? I'll show it to you anyway, don't worry. I'll show it to you afterwards. Okay. Stables. Right, so for power factor, you typically want to sketch a right angle triangle like this. And this will represent P, this will represent Q, and this will represent S. Okay. So the first thing we need to do is obviously get our Q based on of our S. So how do you suggest we do that? We need to find Q, because Q is all about the reactive power. This is for the condition as is. We need to find Q1. Let's say it's Q1 or Q current. Or I don't know, Q1. Let's call it Q1. So how do I find my Q? Oh. We've got let's find our angle. So our angle over here first is 0. We have to convert that 0.75 lagging to an angle, which is 41.4096 degrees. Can someone find my Q of the reactive power which the motor is producing? Someone quickly get that for me. Just a warm-up problem, because I will show you exactly how the question will all look. So can I get my Q? Is everyone following so far? Is there any questions? Okay, Tsepo, Mosipo, and Mr. Mudau, can I get that Q quickly? Is it correct, guys? 4.409 kVA, kVAR rather. So it's 4.409 kVAR. Okay, are you all happy with that? 409. Okay, so that's the power required to produce a magnetic field, which obviously is useless to us. It's the foam in the beer. And what happens is we ask the barman, can you please add some more beer, which essentially this capacitor does. And then now our angle, we have to find our power factor, our new power factor after the capacitor banks are installed, right? So because of that, and you get 18.195 degrees. Okay, so let me use another color. So that means this angle is no more 41.496. It now is Q, sorry, not Q, phi 2, assuming this is not phi 1. Okay, so we have another triangle here. Cool. So what you have to do now is find Q2. What's important to note that the power still remains the same, right? So we're still getting the same power in terms of that, but you're not getting the same reactive power. It's all about the kVAR essentially. So let me look at Q2. So how do I get Q2? So this angle now, that's phi 2. Let me just erase this here. And this is equal to 18.195 degrees. Okay. Let me get that other one. So P still remains constant for both conditions. So let me get Q2. What is my Q2? Anyone? Q2, please. So you can take P. it's a P10 18.195, I think. Yeah, I should get 1.643. That's correct. You guys can solve that. 1.643 bar. K-bar. Okay, so what we have to do now, once you have your Q2, what essentially we have to look at using another color over here is this is the changing Q. So this changing Q is what the capacitors actually bring in, right? So reverting back to this equation, once you have a changing Q, it's quite simple, nothing fancy here. Because so basically what happened was at the first situation with Q1, where the motor was running at 5 kilowatts at 0.75, we added capacitor banks and it pushed up the power factor. So it's actually running at a power factor 0.9 lagging. So we need to find what are the value of the capacitors added, connected in delta. Yeah, essentially that's what we're doing. So we needed the changing Q from before and after, which is essentially we subtracted 2. So can you guys quickly work out my capacitor value? So what it'll be the individual capacitor value. So the capacitor value. Oh, it's talking about changing Q. Changing Q would be 4.4. Remember, it's in kilowatt. Yeah. So I'm not sure that is 4.49, 1.643. 1.643. No, it's going to be 4.409 minus the 1.643. So Q is 2 point. What's happening? Oh, my bad. I see I had a power factor of 0.0. Yeah, I see. So cos 0.9, sorry, not 95. Yep, thank you for that. So power factor 0.9. I don't know why 95. Cool. Thank you. So power factor is 0.9. So the angle here is 25 point. I could have just kept it like that, but anyway, for the sake of the question, 84 degrees. And we can just change all of these here. So can I have my new Q2 again? Thank you. Yeah. Okay. So that's Q2. Q2. Let's erase this. Q2 is simply P times 10 that, and it'll be 5 times 10, 25.84. $2.42, that's correct. 2.4216. And yeah, changing Q would be the difference. So can you guys compute this capacitor value for me? So we have, okay, you guys can just quickly get that. So what is my capacitor value? Let me go check the answers here. Oh, they want the K-var value of each capacitor, but I have a different answer here. I don't know why. Strange. Anyway, you can just V and oh, we don't have the frequency. That's what's missing. Okay, so let's assume for a frequency of let's make it 380 volts. Oh, sorry about that. So we can quickly compute, and this is obviously connected in delta. It's just an example. Okay. Cool. Because, like I said, there's a typically be an add-on on the question, and you'll see in the next example. It's all integrated. And just check all the stuff I've posted on Blackboard in terms of questions. There's a few tutorials and a few questions to do. And if you're not sure, you can just ask me, like I said. But everything we cover will essentially be the, you know, the what's expected essentially. At least for the next chapter there, we're using the John Bird textbook again. Okay, so what's that capacitor value? So you should say 4 point, and it is kVAR. 4 point, what is it? What's Q1 again? What's the Q1 value again? 4.49. Okay. QVAR is 4.49. So 4.409 minus 2.42616. 3 times the voltage squared times 50 times 3 2 pi. Okay, you should get an answer of 14.603 microfarads. What's mu farad? Yeah, mu f. Yeah, micros times 10 to the power negative 6. Did we all get this? 14.603. Cool. Yep. Anyone else get it? Sweet. Okay. So next, here's another question for you. Right? We're gonna do this one, and then okay, let's rather I'll leave this up for homework for you, then we can just do this one. So we're gonna revert back to our previous question, and what we're gonna do now is we are gonna bring well, what are the so I should actually just revise this of the container ship container ship, so to Unity. Okay, so I'm using the same question. So what we're going to do here is, can someone tell me the parent value, or sorry, the current? No, the power factor basically. Or let's get. Oh, we need the S anyway. Of this whole of all the loads here. S total. Can I have that, please, for this question? So what we're going to do is correct the power factor. Yeah. So can I get S total? Yep.
Is this this is obviously before the motor was moved, or is it after the motor?
Oh yeah, fantastic question. So let's say before the motor. Yeah, just for each second. Before motor. Yeah. Before motor was moved. Thank you for clarifying that. Just wanted to use this question again. Okay, let's see. Before the motor was moved. Yeah, so what is it? What is it? S value and the angle. Okay. Cool. It was 673.1. I need the angle as well. At an angle of something. Okay, minus 18.032. Okay. So what I'm gonna just, and obviously let's just get it actually in. Let me just see my I have the board here somewhere. It was, what's the, it's 117 and oh sorry, it's 640. Okay, cool. So we have 640 at 640 minus what again? Minus J 208.47. Okay, cool. So what you can do here is sketch that triangle now. That's 640. That's 208.472. So that's P. And that is Q. And we have this angle as 18.032. Just a demonstration again. What is, so when we bring it to unity, it assumes that we provide the active power all the way up till here, right? So this value now, especially when we talk about unity, this is changing Q. So this becomes changing Q. Is it clear to everyone? You're going to do one in your own after this now. But I want to just integrate this. Obviously, this is before the motor was removed. You guys understand what you're doing here? Is everyone on the same page? You guys lost. So by the way, unity is cos 0, right? So if you say cos 0, you'll get 1. You can check on the calculator if you don't believe me. If you've got cos, not cos 0, sorry, it's cos 1. Sorry, cos 1 will give you 0. That other way around. If you remember your cos graph. So what it means, it brings this triangle basically to 0. Okay, cool. So what is my capacitor value? I'll wait till you guys give it to me quickly. It's a long day today. You guys are awfully quiet. Let's see, Mr. James, Mr. Mamisa, what is my C value in farads? Guys, are you guys lost? You guys are awfully quiet. Mr. Breed, Muda, Mr. Sima. Guys, are you following or you lost? Okay, cool. So you guys work at the capacitor value? Okay, let's see. If I create Mr. Paul 208.472. 3 times, what is the frequency? 415 squared times 50 times 2 pi. Yeah, fantastic. 1.283 millifarad. Fantastic. Great. So C will be in delta, which is always the case. 1.283. We just write it something else. So the C value for this case is 2.8. 283, yeah, 1.283, sorry. 3 farad. Cool. That's basically that. Okay, so what I want to show you now, okay, so we could have done this question, but I think you guys can do it for homework. I can post the solutions afterwards. I recommend doing this one. And also, there's another question. So all the questions, I think Mr. Timothy asked me, everything you need to know essentially is on Blackboard. You can also practice. There's a lot of good practice, so you can try doing this one. Like I said, and then try doing this one. Right, cool. So what a typical question is gonna ask of you, and this is just basically at the end. I'll show you something now. What I expect you to do is apply, explain and apply power factor correction. So I have theory and calculation, which I'll show you now exactly what theory you must cover. Obviously add complex multiple loads in 3-phase, which you've done. Change an electrical machine to new location, which you've obviously done. Frequency and connection change. So it'll be voltage. What's the other one now again? Voltage and it's, how do you say, star delta / delta. Yeah, connection change, that's what I mean. And then also to determine if there's enough kilowatt to power. Okay, this is, I might integrate that within the type of questions. But if you're wondering what you expect to know, it's something like that or something like this. So you have to find the total load and eventually in the end correct the power factor. That's the gist of this chapter in terms of what's expected of you. Also, like, try the single phase problems. I have some nice single phase problems. Like there's a good question as well. You can also try to correct the power factor with this particular question. There's another one. Did we do this one? No, that's an extra one. We did this one. Have a look at the read stuff. I think I've posted these extra questions already. We've done that. Try this one. This is another good question. The single phase one. We have to find the characteristics. So there's a lot of questions to cover. I'll solve something with really difficult Brownian guys. So here's a nice one. I like these kind of ones, you know, but there's a single phase. Try to do this one. If you look at last year's test, it looked something similar to this. Where was it now? Yeah, it's the one. Yeah. So yeah, so like that. So you can get something like this, like multiple loads, change one load, change the frequency. So have a go with this one. And then in terms of power factor correction, like I mentioned, so just give me a moment. I also wanted to show you something, but I'll share two things with you. Let me just share this with you now. Yeah, okay, just it's just a it's essentially it's 3 marks. So any theories on the slide, plus essentially this is a note which is shared by you, called 3-phase_1. And what I just expect you to kind of read over, and this will be some bonus marks for my students, especially specifically for the first test, like what is power factor, you know, how does lagging, what is the stuff we've talked about, what is mean power factor correction, how can power factor be improved, we can talk about that, why capacitor can be used for improving power factor. So it's just a 2-page document essentially, explaining that. So make sure you go over this. So not a lot of questions, but I do think it's important for you to understand the concept of power factor and obviously correcting it, and also the methods of correcting power factor. So that's what I expect. So I'll go over that. Also on this particular thing, there is this yeah, it's what's the heading? It's 3-phase_1. It's on there. It's under exercises, I believe. So it's just saying everything's already there. You just have to kind of look. Yeah, some questions over here as well. We've done some of them. There's a good one on the circuits. There's one. Make sure you do this one as well. See, there's problem 1, problem 2, problem 3. Make sure you cover these ones. Problem 4, problem 5. Those are the basic ones to cover. But like I said, what you're going to expect is multiple loads, correcting the power factor, changing the configuration. Those are the 3 elements which you're going to expect. And even this over here is quite a good one, where we look at yeah, this question over here, the single phase loads as well. This is also quite a good question. I just focused on 3-phase, but single phase is quite easy as well. And obviously the solution is posted over there. If I need to go over it, just tell me. I'll be more than willing. So go over this, and then check the questions on the slides. And once you go over them, I will post the solutions periodically for them. Okay. And just lastly, I'll just close off with this. I could have solved another problem, but I only have to go practice, man. So yeah, making you guys aware now. So your assignments, like I said, totality 10%. So it's 2 assignments of 5%. I will give you the assignment probably when the 3rd term, 4th term starts, or maybe in the holiday once I finish setting up the exams. I'll focus on just in tests and to create the assignment, and the one will be on the AC network analysis and / Altispice. So you get a circuit, and then you guys are expected to solve it. It's similar to the letters 2 things I posted on Blackboard, and try to get yourself the groups along. That's the best thing I can advise now. It's like I said, this is supposed to be giveaway marks, but obviously it's making you learn the software as well. So play around with it. The second thing will be a research paper assignment. I was thinking of doing something else, but what I'll do there is I will give each student, each group rather, a paper to look at. They're all dealing with electrical, new grids, new types of technology, and you guys will have to basically read the paper, understand the paper, and draft some questions based on the paper. Like a question and answer thing. So again, it's more the element of getting into actually going into research, and so each group will get a different paper, and you guys will have to like read it, and so it's quick. So that'll be end of October. So yeah, if there's nothing else, what I recommend is I'll have to repost these slides again because I'm always updating, like I said. And then after this, we're gonna start on. So that's essentially cancelled over here. Next week we'll start on DC machines. We're going to look at both the generator and motor, and yeah, that's the plan for next week. So it's going to be a nice bulky. It's very easy. It's in the John Bird book if you want to look at it before we start. Yeah, and that's basically all. So I recommend once for tonight, try to solve this one, and then go look at the tutorial and go solve that one. You can also try to solve this one over here. So it's not difficult, just long and big, but obviously, yeah, it's going to give you enough practice. There's also a Word document with some of these questions on there. But again, what's important, explain and apply powerful factor correction, both theory and calculations. Be able to add complex multiple loads you guys can do, and making sure electrical machine is, when it goes to a new location, you're able to do all of that, yeah. And also, if you're able to determine enough power, that's like a bonus type thing, which I'd always do just to check understanding. But anyway, guys, that's all for today. If there's any questions, please ask now. Mr. Wall.
Sorry, it's a bit stupid, but the synchronous motor as using it in to correct the power factor. Is it only correcting when the thing is actually, I mean, does it serve a function other than like just running, or does it serve a function, and does it correct the power factor only when it's running or only while it's connected? You know,
okay,
what are they?
Yeah, so so the first thing is like a synchronous motor can be used for something else, right? A synchronous motor is essentially a motor which spins at the speed of the magnetic field. So it's a motor on its own. It's a good constant speed type motor, right? So when you're running a synchronous motor, and when I mean overly excited, when your voltage, so you generate the EMF, and when your voltage is greater than your EMF, what happens is it goes into another mode, which is essentially the overexciting mode, and it basically produces a leading current as a synchronous condenser. So we're going to touch on it, but my point is that a synchronous motor is meant for something else, but it has the ability to act as a synchronous condenser. I don't know if I'm answering. Yeah, it's not actually meant. It can be used as. Yeah.
Okay.
You want to add something? Try more something.
No,
No,
no.
go for it. No. So it's not only it's a synchronous motor is actually not it's a so when we do synchronous machines, right? We look at the alternator and the synchronous motor. If we do touch on the motor, but the synchronous alternator basically it doesn't have, if you remember Electros 2, it doesn't have slip. So it just has this, you know, the NS, which is it's basically one rotational speed it has. So
Right.
that's hence the word synchronous. It's the
Yeah.
rotor
thing.
is spinning at the speed of the magnetic field, and then then you get asynchronous, which is an induction motor, which has the slip. So nevertheless, so once we do motors, typically on a bigger scale, like on a bigger power plant, they'll use synchronous motors instead of having a shitload of capacitor banks. Because I mean, you can't have these massive capacitor banks, like massive capacitors to correct, you know, like big voltages and stuff like that. You're talking about, I don't know how much kVA exactly. So yeah, it can be used as, but what a synchronous motor is essentially good for, it's a good constant speed, what do you call it, motor essentially. So if you want to have a constant speed kind of the motor, if you want to control it a lot, like you know, you have your induction motor you can control using VFD and things like that. If you want like a constant kind of output, you're gonna go for synchronous motor. I'm not sure if they use these for propulsion. Yeah, me and we had a discussion about that. So yeah, that's all the thing. I can send you a note on synchronous motors if you want to have a read on it.
All right, I'll look it up. I'll look it up, especially the propulsion question about it. If it's because I don't know anything about electric. Well, I know very little about electric propulsion.
Yeah, cool. And that's the purpose of the assignment. Okay, guys, we done the official lecture here, so I'll just I'm gonna share a few things with you guys just to show you what I'm trying to like show you guys in terms of. So I've got some papers over here. I want to show you. This is just extra bonus stuff when the lecture's done. Where's my research quickly? My research, but the papers in particular, TMS, 2021. Okay, cool. Let me just show you. No, I'm gonna see it now. 20. Research. Yeah, so let me open up one paper. One of the papers a particular group will look at. Okay, not, I didn't want this one actually. Yeah, okay, here we go. So let me just open this, share this with you. Yeah, so here's one paper where we're looking at one group is definitely on this paper. It's basically the optimal sizing of a hybrid PV diesel battery in a ship power system. So essentially it's an optimization study looking at how we can propel the ship using a combination of solar PV, diesel, and obviously your energy storage. So that's one paper. I'll show you. So that's what the idea is basically. That's what they're proposing. You have your AC bus, which produces the diesel generally on the AC bus over here, and you have a transformer obviously to step down for your AC loads. Then you have I guess a converter of some sort to go from some rectification going from DC to AC, from AC to DC. Sorry, we have a DC bus, and then on your DC bus you connect your PV panel and your battery. Obviously you have some DC loads on there. This is just like one, and they're just talking about a control strategy. So what they do in the paper is that they look at how do you travel from Aden in Yemen to here in China, this place called I don't know how you pronounce that, and they look at this. What's one of the tricky things of using solar PV in particular is that you typically want your PV panel to face at a particular angle, and for maximum amount of solar radiation. So as it's traveling around here, you'll find out that the radiation will obviously vary. But I don't know exactly the full details of the paper. Obviously, I have to look at it. And they're basically predicting of how much power output you can get, blah 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 blah, things like that. That's one type of thing. But you're talking about hybrid propulsion. I'll open that now. I had some papers open now. Okay, this is just not that one. Just to show you an idea of this one. Yep. That's the one I looked at last time. Yeah, so design and control of hybrid power and propulsion of the smart ships. Okay, there's one I'm looking for in particular. Right? This one. So this one is a typical propulsion layout, where you have your 4 gens, your diesel gens producing the AC on the main bus, and what you typically, so that's a bus number 2. You have your transformers at 3. It's your 3-phase transformers, and what you typically have is frequency converters on the thing, and then you also have your propulsion motors. So I'm not sure exactly what type of motors these are. I think the paper will talk to that. And obviously 6 will be all your normal standard loads on that thing. That's a typical propulsion system. You can, if you want this paper for your group, you can probably get it if you want to learn about it. Here's another type of arrangement where they have separate phase shifted bus bars. So you have 2 different types. There are 2 chains running on that. Another architecture would be, they're talking about a few things here. This is like on the research domain. I don't know if guys are implementing this already. Another type would be your hybrid propulsion, obviously, which is like quite common. We have your diesel gen there, and that's your propulsion. And obviously you have your chains here, and then you have, I think I have a picture of this one, your transformer and your frequency converters, and then, or what generator motor, whatever this is. I'm not sure what MG is exactly. But that's another one. Let me just open another paper as well. So I've got a few papers. Okay, didn't open this one already? Yeah, I did. This one. There's something else. Anyway, yeah, there's a few good papers. The other one, which I want to open, actually, I'll show you now. DC. I wanted to bring it up in the DC ships. They're talking about having a. Are you still there?
Yeah, still yeah.
Okay, cool. I was wanting to help you. I had it open early on. Yeah. So this is another paper I'll be giving to students as well. This was published in 2018, but they were talking about having a DC grid basically for ships. And like about this one in particular, that they'll show you, like for oil carrier, for instance. This is what an AC one would look like. Because on the AC side, you've obviously got your bus at a certain voltage, then you've got your converters over there, and that's how it typically looks like. And obviously there's your filters, your harmonic distortion filters, and then for DC you kind of eliminate the transformers, obviously, because you don't have to now transform power, and then you have obviously you have to convert with some kind of inverter to your AC. So this is just they give you the one type for pipe layer ship and for dredge over here. They're just playing, and they're just talking about the essential benefits. And just in summary, obviously you guys need to go research this, is that it has benefits as variable speed frequency operation of gensets. Yeah, it's quite easy to control DC motors. There's also removing from rectification in VFDs for motor controls, reducing weight and volume, eliminating harmonic mitigation. So there's less harmonic distortion with the sine wave. You also can integrate DC power sources directly to the bus, and let's say unnecessary for additional small generator saving costs. So they just, within the research domain, they're proposing, there's a lot of other things as well you can have a look at here. There's also like freedom of no reactive power, freedom of frequency, and also less harmonic distortion and of increasing power quality, because you want to be dealing with the power factor, blah blah blah. So anyway, that's just where people are going with this. This could be in the next 2 nodes if it's possible. Yeah, I don't know. Anyway, you want to say something?
Are you going to post this? Or where would I? Yeah. Are you going to post this kind of stuff?
Yeah, I'm gonna post it on Blackboard. So, like I said, each student will get a paper, or group of students will get a paper, and you guys will read and extract some information from it. Yeah.
Okay.
I can show you. I can actually show you where to get. Yeah, I can actually show you where to get the research and stuff. You can always engage with me on something if you are interested.
Oh, it's interesting stuff.
Yeah, no, it's crazy stuff, man. But like, I mean, this is like in the research domain, and maybe in the next 10 or so years, depending if things get cheaper, to become more, more prominent. But yeah, I'm trying to get people to read more, and So now you guys get a ship and you guys on board a ship and the technology is there already. But I think there is a shift going into like hybrid propulsion, and so I mean the content itself is not at this particular subject. Was the old diploma, that is why it's this content. But when I'm on the bachelor program, I'm gonna give the ladies a move, say they. I don't think they're gonna cope anyway. I mean they're gonna be their kids, but yeah, we'll see. But anyway, yeah. But engaging on WhatsApp, you know, we can have discussions on things like this. Is Mr. Lecoq still there? Murad, you want to say anything? Yeah.
Yeah, I'm still here.
Oh, cool.
So this Altispice that I downloaded, my Altispice doesn't work. It opens the program up and everything, but I can't access any of the things on top. It's all like, you know, that light gray.
Yeah, do you have an Apple laptop or something?
No, I got an Acer.
I'm not sure why.
It just doesn't. I can show you a video. It just doesn't allow me to click on any of the tabs on top.
Okay, so let me. It doesn't make sense though. I mean, it should.
I can take a video and send it to you on WhatsApp. What I mean.
Yeah, cool. So now it's cool. That's fine. You can do that. Yeah. Okay. Yeah. So we'll hopefully touch on synchronous motors in this time. Then you can have a look, see what's happening here. But anyway, guys, thank you for tuning. Hope you guys learned something. Keep practicing. Cheers, Mr. Mongo. Yeah, I have to make a new page on it, on Alti. But yeah, get down on Altispice. It's not me giving anything too heavy. Fortunately for you guys, I've given you something crazy, but yeah, it's not that bad of a course. It's actually quite easy. Okay, guys, cheers. See you next week.